Ever wondered why some electronic components, which seem so straightforward in theory, often come with a hidden layer of complexity when you dig a little deeper? Understanding these nuances is key to mastering electronics and designing truly robust circuits. Zener diode dynamic impedance, often denoted as Z sub Z, is essentially the opposition a Zener diode offers to a change in current flowing through it when it is operating in its reverse breakdown region. Unlike a fixed static resistance, dynamic impedance describes the diode's resistance to small signal variations, reflecting its ability to maintain a stable voltage. This dynamic impedance exists because a Zener diode's voltage in the breakdown region is not perfectly constant. It changes slightly with variations in the current passing through it. It arises from the internal physical mechanisms of Zener breakdown and avalanche breakdown within the semiconductor junction. The dynamic impedance is effectively the inverse of the slope of the Zener diode's current voltage characteristic curve in its breakdown region, indicating how much the voltage changes for a given change in current. For practical application, understanding dynamic impedance is crucial for designing stable voltage regulators. You can calculate it by dividing a small change in the Zener voltage by the corresponding small change in Zener current, often found in datasheets for a specific operating current. A lower dynamic impedance indicates better voltage regulation, meaning the Zener voltage remains more stable despite fluctuations in the load current or input voltage. It is also important to note that dynamic impedance is not constant across the entire breakdown region. It tends to be higher at very low Zener currents, near what is called the Zener knee, and generally decreases as the Zener current increases. This characteristic influences the power dissipation and temperature stability of the diode. Typical values can range from a few ohms for higher power Zeners to tens or even hundreds of ohms for lower power or higher voltage Zeners. Ultimately, recognizing and accounting for Zener diode dynamic impedance allows you to design more precise and reliable voltage regulation circuits, ensuring your electronic systems maintain their specified performance even when operating conditions vary. It highlights the real-world behavior of components that appear simple in an idealized circuit diagram.